And for today, I will try to solve all the challenges like from start to finish, because I felt like last week at the very least. I mean, of course, last week we didn't have. I mean, not last week, but in the last module, we didn't have enough time to go through all the challenges and try to solve them like first first step till the end. But now for this poem, and also because I noticed that not everyone tried the challenges, or at least this is what it seemed, because I didn't receive solutions from everyone. Only 8 people did submit at least one challenge, which was like almost half of how many people submitted at least one challenge last time. So I will try to go through all the challenges one by one. It is okay, Donk. It's okay. I will try to do my best through this 2 hours to explain everything, and yeah, it should it should be fine after these 2 hours. I mean, I'm gonna try to solve them live, so you guys will have a better understanding and a better idea how to approach these type of challenges. Also, I will solve all of them manually. I'm not gonna use any tools. I'm not gonna use any shell craft format crafting mechanisms. I'm just gonna do everything purely by hand. Do you guys see my screen? Okay, yeah, no, I'm not sharing my screen yet. I will share my screen in a second. Oops. Yes, everything gonna be solved in scripts. I will craft the scripts live. We will do everything live. I think we can start already. I will share my screen. Entire screen. Do you guys see my screen now? Okay, nice, perfect. We will start with the first challenge. Yeah, it is okay. It is okay. I mean, I didn't give much information regarding Pound Tools because I thought the 2 hours lecture during the preparation of the cybersecurity day was enough. Also, like Pound Tools, I cannot give everything related to it in one lecture or like in one link or two. It's more of how much time have you been using it. So the longer you're gonna use it, the easier it will get. And yeah, anyways, we will get started now. We will start with the first challenge. We're just gonna go through it real quick, and then I will start solving it live, as I said. And yeah, we can start. So in this challenge, I'm just gonna take a look directly into the source code because you guys know how to decompile this stuff, right? I mean, you're just gonna use IDA or Ghidra or Binary Ninja or literally any other tool. If you don't know how to do this decompilation, I'm gonna do it for the first challenge, because for the first challenge, I actually did overwrite the source code with the solution of someone, and I lost the source code. I just did check it today and I found out that I actually lost the source code, but it's fine. We have the binary and we can decompile it. We are reverse engineers, so it's okay. But for the first challenge, we're just gonna take a look into everything. So basically we have a main. The main is asking for inputs, and it takes this input to just like null terminated. It just compares it with quit to stop the looping, and then it's just gonna try to print our variable directly. And as we said last time, the printf, if it's applied directly with a variable, it is super dangerous. And even if you like even while compiling it, the compiler will complain and will say that this is insecure and you should not be doing this. So I think everyone noticed that this is actually the bug in the whole binary, and this is what we have to exploit. And how we're going to exploit this, it's obviously using the different type of formats. The goal of this challenge is to basically leak the base address of the program. Of course, we cannot directly leak the base address, but we can leak a relative address and then calculate the the base using the offsets, because the offset is always the same. By the way, if I'm going way too quick or you have any question, just throw them in the chat, because otherwise I'm just gonna continue till the end. So please, if you have any questions, just write them right away. Don't wait for me to ask. Okay. Okay, let's continue. Same thing with libc. So the libc base is also going to be calculated on the fly, which means we have to leak at least one address. And based on this address, we're just going to deduct the offset from it, because the offset is always the same. And then we're going to calculate the RAP, which is the instruction pointer. And last but not least, we're going to leak the canary. Okay, let's first start just by some simple debugging, just to know what are we dealing with. Oops. Challenge 1. So this is our binary. I'm gonna do disassembly main, because we have the bug in the main, and this was actually the print inputs. We can look for the print input within here. Why am I calling when? Oh, I am in the challenge 1, my bad. We can here go to challenge 0, and then from here GDB challenge 1. No, what am I doing? 0, GDB challenge 0. Disassembly main. Everything so far is good. We can take a look into all these printfs. This is the compare that we have here. So basically the first printf under the compare is this one. As you can see, you don't always have to decompile to know what you're doing. Just by looking into the stuff here, you can relatively understand what is going on. Also, if we do check sec, we will see that everything is pretty much enabled. We have the canary, we have the we cannot execute anything on the stack. Pi is enabled. That means the address is going to be modified every time we run the binary, which is okay. I mean, this is also the reason why we have to leak an address before we can calculate the base. Now we will try to breakpoint here, because it's not stripped, so we can just like calculate this relatively. So we can do base main, break main plus this 188. So this will set a breakpoint on this address here, and I'm just gonna run the binary. I'm just gonna try here to give it anything relative, because I think I already went through the printf that actually takes the input. No, yeah, never mind. So it actually takes the input here before running the printf. My bad. As you can see, this challenge 0 and challenge 1, I didn't solve it myself yet. I tried to make it as much realistic as possible. So I know they are solvable and I know how to solve them, but I didn't do them myself yet, except for challenge 2, because I wanted to make sure it is actually solvable. But challenge 0 and challenge 1, I didn't do them yet, so I'm gonna do them now. So it's actually my first time doing them, and hopefully we can finish them within this next 2 hours. Okay, so just gonna give it Control P, just to take a look. Now we're just getting the feeling about the binary. And now we did actually hit the breakpoint that we did talk about, which is this one here. And now we can start inspecting the binary. So when what I mean by a base address is always this address here. This is where your program actually starts, and this is the address that we have here. This is a little bit weird, because normally Pi is enabled. This should not be the correct address. But I will take a look into that in a while. And the second thing, this is the base address of libc. As you can see, you see libc here, and this is how you know that this is the base address. This is the first section. All of these are sections in the memory, and this is the first section in the libc. And here we have the stack, and from this you can already tell that this is actually weird. Why these addresses are not randomized? is enabled. It looks weird why it's not randomized. I mean, even in GDB, it should look like it's a run. I mean, it should show you the randomized data. It has nothing to do with the GDB. But I will take a look into that. Maybe because of KAR. It doesn't matter. It doesn't matter. I mean, even if I just run something like this 0 and they do just start, if I do VM map here, I should see like a different offset. I think it's because ASLR is not enabled on my machine. I assume this is the reason. Let me just check. We can do everything together. How to check if ASLR is enabled on my Ubuntu. Yeah, okay, so this was the cats 2. What does 2 mean? It's actually full ASLR. That's super weird. I don't really get it why it's not randomizing it, but anyways, for us it's gonna be the same thing because I will try to calculate them on the fly either ways, whether they are fixed or not fixed. I'm just gonna try to I mean, even in GDB technically it should work, but maybe let me try something. Let me try to attach it with GDB. Now we're gonna start with from pound import all, start right, dev exploits pom, just pass here, exploit, just call it here, and then here in exploit we have p is equal to process, and we have the binary. It is actually giving me the first stuff, which is pretty much good. Okay, it's starting to write everything for me. I don't want it to write everything for me, so I'm just gonna disable it. Oh, this is cursor. I have to go to the settings to disable it. Okay, but I will not use tab as much as I can. What does it take as inputs? So when you run it, okay, we can just read until this part here. B to not, so that it does not complain. So we actually read until this part, and then let's just send a %p, and then give it %p. Okay, so the next line, okay, a receive line is strip decode, because we are receiving bytes, that's why we have to decode. Leaked, this is the leaked address. Just gonna print it to see if I'm doing everything correct. Immediately remove this, and we don't have to close it, closes automatically. We don't need this. Let's try this. So Python, so run it. Okay, so it's actually working. Okay, maybe GDB is doing this, as you said. Maybe GDB, this is something internal in GDB, but it's still weird. Even GDB should not be able to do something like this. But we can bypass that by using GDB through pound tools. Here it for sure gonna be modified. GDB is equal to script. I always like to start my scripts like this. Pom. But I don't need this. We're gonna break in what we said, main plus 188, right? If I'm going way too fast, just let me know again. I'm just trying to solve everything the way that I would solve it in any CTF. So I had the breakpoint here somewhere. Oops. Break. Yeah, here, 88. Okay, this is correct. And then we're just gonna continue. This should work now. It runs because it runs only in tmux. This is GDB debug only runs on tmux. So we're just gonna try it with tmux now, see if it's gonna, okay, it started the instancer. This is going good, and we actually did hit a breakpoint that we did sit here, and we are actually okay. Now the addresses are randomized. Okay, now it's actually correct. So if we do vm map, the address here is randomized, and the address here is also randomized, and everything else is randomized. Let's try to run it again just to make sure. Bam, 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 bam. Yeah, the address is randomized. So now we are on the right track. Okay, good. Now we made sure that this stuff is randomized. As I said, this is the base that we want to achieve. So while testing later on, we have to see that the address that we did leak and calculate should be the same as this, and the same as this, and later we will see whatever comes after. Okay, now we will start with testing. So before sending this, I'm just gonna make something called payload, which is what is gonna have like everything from now on. I always start with this here first part. It's always gonna be my padding, because you will see why we need padding, but I always leave one empty like this padding, and then I start my actual inputs. Okay, so this one is just gonna be empty, and under it I'm gonna start with the actual stuff, and right under it I'm gonna put like a couple of A's just to know where I am on the stack now. Couple of A's, couple of B's, couple of C's. And for now I think that's it, because I just want to see first where I am on the stack. Let's stop this, run it again. We did hit the breakpoint. Now after hitting the breakpoints, I would try to go one step further, because I don't want to be stuck in the printf within main, because the stack is gonna be different when we enter printf. So after the continue, I'm just gonna have SE, which is single instruction. I'm just gonna go one single instruction under, and now we are within the printf. So now if I inspect the stack, if you remember what I said last time, I'm just gonna make this bigger. If you remember what I said last time, when you do xg, we do examine 8 bytes, and what we want to examine is the stack. So RSP is our way to go. And now if we do 50, we see that yeah, actually we are super close to the top of the stack. No, never mind. This is just the inputs. It shouldn't be. No, yeah. We are super close to the top of the stack. As you can see, this is our A's, our B's, and our C's. Okay, for now, this is good, which means like anything that we will print later gonna be everything which is under this. So this is what we will, this is our target of reading. And now we can already notice some stuff. So if we do vm map, we see that, okay, this is how the addresses on the program start. They start with 5C, 99, 8B, 91, because these 2 bytes, they're going to be changed. But this part here should be the same, or maybe this one will be also modified if you overflow this part. But I assume this part going to be the same. Let's look, and we already see, like, look, this is an address. This is a valid address on the stack. This is a valid address of the program. So if we leak this and we calculate the difference between this and this, it should be already enough, and it should be already our way to leak the base of the address, the base of the program. So I'm just gonna print this. I'm not gonna print 50 now. I'm gonna just print 30 and see if there is anything here. Let me just go up, see again what was that. Okay, 5C99, 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 8B91. I'm looking at this part here. 5C99, 8B91. Okay, so this address here, let me just pick it and take it here. This is the address that we saw in the stack, that it looked like it's in a valid address on not the stack. Yeah, the address is in the stack, but this address is pointing to the program. So we have the address of the program. Now we want to check again what was the base, just to calculate the offset. So this was our offset. So we're just gonna do minus this, and okay, so this thing is already did it for us, but normally this is what I do. Just open like Python here in another terminal, just do this, and I like to have it on hex because it makes sense. And okay, so this shit is actually not calculating correctly. That's why you have to do stuff manually. Am I going way too quick? I feel like it is already the slowest that we can go. I mean, am I talking quickly, or the steps are fast. Because so far we still didn't do anything. We just did take a look into the stack. Okay, let me just repeat again. So basically, we want to leak a base address of the program. Let me open VMap again. So we want to leak a base address of the program. We want to leak the libc and the REP and the other stuff. Now we are only interested with this. So we want to get this somehow dynamically from our script. To do this, first we have to try to leak something from the stack, which is pointing somewhere here or close to here, which is in our example here, this address here. And I'm just trying to calculate what is the offset, because this offset here is always the same. This thing here will not change. Doesn't matter what we do. Like, it doesn't matter if you run your program a million times or a trillion times, this thing here will be always the same. So I'm just like right now taking the two addresses that I am interested in and just trying to calculate the base. That's it. So just two addresses. This is the base of the program, which is our target. Because if you want to look at it from another perspective, you can just, okay, nice, turn off autocomplete. This is what I wanted. So if you want to do like this on the other way around, this address is actually the base plus this offset, and it gives us this. This is what we can leak. So to get this back again, we're just gonna do a minus. It's a simple subtraction here. Okay. Now, I don't like, I mean, I like to do everything like dynamically, because I mean, right now I'm going slowly, explain everything, but normally in just one GDB run, I get literally everything I want. I mean, right now I can get literally all the offsets, I can get all the addresses, I can get everything in one GDB run. But now I'm not gonna do it because I want to go through everything as slow as I can. But that was the reason why I use GDB better than object dump. I use object dump mostly if I want to look for gadgets. Gadgets that are used when you are roping. So when you are looking for, and gadgets are basically instructions that end with a return. These are gadgets. For now, this is not our main topic. The gadgets that are, as I said, they are used in roping, return-oriented programming. For now, just forget about this. Object dump is also a valid way to do this stuff, but I just do this stuff with GDB because for me it's more practical. So as I said, because it's in one run, I can do everything. Yeah. So this was our main. This was our target address. Now we want to see where is this address actually, and to do this, technically, I mean, this is not a 100% way to get it, but technically this is how I do. So basically I take this address here, just again do hex because it just makes more sense. No, here I don't need hex, I need something else. I need the division, and I just do minus this and I divide by 8. So what I'm doing now is I'm trying to see what is the offset of this address. What is it? Yeah, here. I want to see the offset. And what is the offset? The offset is basically how far is this address from the top of the stack, or not from the top of the stack, but rather from the indices. That's the indices that we can leak with the the indices that we can leak with the percentage %P. So these indices, they start from somewhere. Mostly they start from the registers and then they go through the stack. Okay. And now I just want to know what is the index that I have to give here, the X that I have to be putting here to leak this correctly. So to do this, first I just take this address, I just decrement it from this address, and then this, how much is it? So it is 18. So normally it should be 18 plus 5 plus and minus. Why plus 5? Because we have 5. So in the conventions of assembly, if you are trying to call a function, so you have an instruction call I don't know, win or call printf. Before like this call is put into the stack, you have to have RDE contain something, RC RCE no, not, yeah, RDE, RCX, RDX first, RDX, RCX and R8, R9, and R10. These are the conventions. So the first argument of the printf gonna be RDE, the second one gonna be RDX, then RCX, then R8, then R9, and then R10. This is the convention. That's why we have +5, because we are jumping five positions. That's why I said plus and minus, because sometimes it's also +1, and because we're starting also from 0 and we are talking about indices. That's why this is a +5. I know there is 6 elements here. Okay, does it make sense? But just like as I said, this is not guaranteed thing. Sometimes I run into issues like there is a +1, -1, +2, -2 indices differences. That's why I always check it back and forth, and this is what I'm gonna do now. So we have our couple of A's, B's, and C's, and right under it I'm just gonna have payload plus equal B, and then I'm just gonna have percentage, how much we said 18, so I'm gonna do the 23 $sign P. I'm gonna try to leak the address 23 and see if it is actually this one, or we are off by something. Okay, so let's try to run it and see what is gonna give us. Let's continue. We're just gonna continue and see the address. Okay, actually we did get the right address right from the start, you see. So in this example, so the +5 check did work directly, but as I said, it doesn't always have to work directly. Sometimes you have to do some checking like you do here, +1, -1, but it shouldn't take more than that. Okay, just to make sure again that we have this right address that we talked about, we will take a look into the stack. So we will do again this thing here. This was the address that we are trying to leak, so I'm just gonna copy it first and then continue and see. Okay, this is actually the same address, as you can see it here on the right side. It's the same as the one on the left side. Okay, so now we are happy because we got our first payload, because we got our first leak. So this one here should be the leak from the base, and now I can actually correctly calculate the base of the program. So now the base for me is equal to leaked minus what we did calculate before here, this. And now if I print base here, the base of the program is can just print it like this. Do this base, it should give us some couple of zeros at the end. Let's see if what we are doing is correct. And supported operand type. Okay, it's because we are reading this. Okay. So we have to read this back into a number. This is actually a string, and to do this we have to use int to convert a string back into an int. Now it should work. Let's try again. Leaked, why? Format base 16. Oh, never mind. So it's actually also reading this part. Okay. And by the way, you have to actually be careful, because now if I remove this thing is not going to be a valid index. Do you guys know why? Can someone in the chat tell me why? If I remove this part here, this thing is not going to become a valid index. Yes, exactly. So if we run this back again, and as I say, as I did show you guys before, if you do this, you see that actually some space here is taken by this part here. So if we get rid of this, technically, instead of reading this, we have to read this part. I think we have to read this address now. We will just see. I mean, we are here just learning, we are just testing, so let's just try it and see what are we going to read now. First, let's check the stack. As you can see, we don't see this part here, and it was pushed upward. I think the address is this one or something. I don't know. But if we continue, as you can see, yeah. Okay, so this one is actually trying to calculate, and this one is not printing with the hex. But you get the idea, right? And leaked, it should not be here. Leaked address, it should be here to make the difference what we are doing here. Okay, now I will just leave back this A's because it, okay, I'm just gonna leave back the A's and the B's here because it's not gonna make any difference for us if they are added there. We are not overwriting anything in this specific binary. Also, to not run GDB, we can just do it like this. So now I have to run, technically I should be running it directly, yeah. So I'm just gonna get rid of this part here. So I'm just gonna do split, and then do split with this. Oops. And then just gonna take the first element. I'm doing it in an ugly way, I know, but it doesn't matter. You just have to do it the way you like and the way it works for you. For me, it works right now. As you can see, I'm linking the address correctly. And I am pawning right now. I'm not writing a read program. So as long as it works for me, I don't care, okay? Is it clear now how we can leak a base address? Because it should be the same thing for it should be the same thing for libc, because we want to use our time efficiently. I'm not gonna do the libc. It should be the same thing, right? We can jump over the libc leak, right? Because it's also the same thing. You just have to find the address of libc on the stack and just find the index and do the same thing again and again, okay? So if you do this here and we do a VM map, we see that, okay, libc start with 7760. 7760, yeah, you can see that there is already an address here and you can leak it yourself, okay? Where I see libc base, you don't see it in GDB. I mean, you see it in VM map. So VM map, you see here, this is our program. This is the name of our binary. These are the sections. These are the entries of the binary. The base is always the first one. So the base of libc is actually the first one here. Okay? Does it make sense? That's a good question, Dong. I'm also not entirely sure. I think it has something to do with GDB optimization, or because something is already stuck on the stack. Sometimes it's not on the stack, something like this. Not stuck on the stack, but stuck in the registers. Maybe because of this. But there is always this plus and plus one minus. But it should never be more than plus one minus one. It should never be more than this. Okay? What do you mean I am writing more than 6 bytes? Yeah, I mean, it doesn't matter. The last, I mean, these 4 bytes, they're just gonna be filled with they're gonna be padded with the zeros. I don't understand the question. Like, what is wrong with writing more than 8 bytes here? I mean, I'm not overwriting anything now. I'm using P. Yeah, I mean, libc has more, but it doesn't matter, as I said. The offset of libc is calculated with a minus, so it's, I mean, you're just gonna get the correct offset and just deduct it from it. It shouldn't cause any problems. And what do you mean by you? Yes, so the offset is $2 difference. Yeah, yes. So yes, actually, so if you get rid of this, we have to actually go down by 2. Yes, you are correct. Yes. Yeah, you can put here even 1A. Listen, this is not something mandatory. I'm just putting this now so that you guys see it on the stack. I mean, you don't really have to have this there. This is important when you are putting stuff on the stack, just so that you see where is the address on the stack. Like in the next exercise, we're gonna put an address on the stack before we actually overwrite it. And in this case scenario, it's important because with this we know where is the address. But otherwise, it's not really mandatory. I mean, even in that case scenario, it's not really mandatory. I mean, I'm just saying. Okay. I completely forgot how there is a command that shows it. I thought it was frame. Maybe it is. Okay, I cannot view more than. Yeah, info frame. Okay. Yes, okay. So I remembered frame, but it was info frame. Thanks. Thank you guys for the information. As you can see, even like this stuff, you can forget it easily. So it's you have to learn how to actually find the information and use it on the way. And as I said, right now, I'm just trying to solve everything on the fly so that you see that even for me in the during the like doing the CTF or like during these type of challenges, it comes to my it comes to me that I forget some stuff and I have to go look for it and then do it again on my own. You see? So it's totally fine. Okay, now we see RIP. This RIP, it should be on the stack. We just have to find where it is. I mean, not yeah, so we just have to find where it is. And to find where it is, you just have to go deeper on this look up. Let me just put it here on the side. It should be just a bit down. Do you guys have the address director of this? Because for like to find the REP, it is usually better to do it in a script because most of the time it's a little bit further down. How did you guys do it? Did you guys write a script or did you guys just keep leaking with a bunch of percentage %p? Script. Okay, nice. What about the rest? Both ways? Nice. Can you tell me the index so that we don't have to go through it? It should be a little bit further down, right? So what is the index again? Okay, we can just try to print 100. 51. Okay, now we actually did hit the addresses that are close to the REP. None of them is actually REP. To see. Shouldn't be that far down. No, it shouldn't be that far down. I'm actually reading right now something that I shouldn't be reading. Let me look again at the first 80. I think I just missed it. It's somewhere. It shouldn't be that far. Hey. $51. Oh, okay. I was looking at the wrong bytes. Okay. C7A8, C7A8, C7A8. I mean, you can calculate it, but you can see it also on the stack because it should be on the stack. It's the last um, address. Oh, I get it. I think I know why. Wait, let me run this again. Let me do it again. Yeah, I get why I don't see it. I have to step in first. Let me make this smaller. Don't see even where am I. Okay, now I am inside the printf. Now if I do info frame, I get this here and get this here. 6.8. No, we should be in the same frame. Oh no, my bad. I think I got something confused. So yeah, okay, never mind. Sorry guys. Actually, yeah, I got confused. So basically, this address of the REP, it contains the address of the return, and the address of the return, we can see it on the left side, not on the right side. My bad. So 6.8 should be here. So the address of the return should be what? Yeah, this is A. Okay, this is A4. We need A2. A268. A268. Yeah. So this is actually the address of the return order. Yeah. Okay. Yeah. My bad. So this was actually the address of REP. Yeah. Okay. Yeah. It should be calculated. Yeah. Yeah, you are correct. TR. I don't know why it feels kind of weird to say your name. It feels like I'm insulting you, but yeah. Okay, so you did calculated with the Fini and RSE leaked address. What do you mean by it was the same for you for like RSE leaked address? I mean, you can calculate it basically with literally everything. I mean, the moment you have an address on the stack, you can calculate this again. Because again, if we do VM map, now we are on this place here. Just so that you know where we are right now. We are leaking stuff here, but we stand here because we are on the stack. When we do RSP, this part here, all of this here is actually here within. Okay? What do you mean by start of printf rep is RSP? Instruction pointer. Yeah, the start of printf. Yes, it looks at RSP because yeah. I'm looking at the picture that Matt did send. RSELIX string. Oh, okay. I think you have something wrong there, Matt, because this address is the base of the address. So you have the content of RSP. It doesn't make sense. Matt, I think you have something wrong there. The address of REP should not start with the same offset as the addresses of the program, it should be on the stack. So it should start with the same offset as the stack. Like this part here should match the stack that we have here. Otherwise it's wrong. Yeah. The easiest way to do it is to leak a stack address and just deduct it from the other address to get, like, you look at the offset between this part here and an arbitrary stack address. Wait, let's look for an arbitrary stack address. It's 7FFEB, 77FFBB. Okay, so we have this address here. We can take it here. Gonna deduct it from not the base. We need this with info frame. Again, the addresses relative to the base, they change. In the stack they change, but relative to each other it's always the same. So we're gonna deduct it from this, and this is the offset between them, so we can calculate it based on this. So now let's have a new part. Here we're just gonna repeat the same setup, or we can put actually this into we can put this into another function, leak func program, and the index code. So this is the first iteration, and instead of print, okay, we will print. We don't have to print it, right? Yeah, we're just gonna return leaked. Now we don't need this part here. Just gonna do leak func. Gonna give it p, and the index was 23, and it should give us this. Okay, I should have specified the REP that I meant there is of the printf itself. I mean, it doesn't matter. So I just wanted you guys to know how to leak REP. Later on in the wild, you can decide which one of them you are trying to leak. But for now, just to understand, like, the whole point is to understand what is REP and how to leak it, okay? Let's test if this is actually working before we continue on. Print base. Yeah, okay, so the base is correct. So what we did do here is correct. Sorry about this. Just to put it, yeah, this is actually already writing here. Here is the base. Sorry. Leak func. Okay. We have to actually find this index. For now, I'm just gonna put 23 again and see in the next iteration which value does it have to be. Minus, we said 400, right? 400, and the REP of the program is REP. So we don't know what is the point again, so I'm just gonna try it like this and see the offsets. The map 7FFE 7FFE, so it was this one. Again, just gonna take this address, deduct from it this address, it's 16 plus 5, it's 21. So this should be 21. Let's check if the stuff we are doing is correct. Now technically we should hit the breakpoint twice, so first continue. Oh, wait. 1 second, we have to let me rerun the I think it's we have something wrong with this sending and receiving. Let me just run it again, just a note. Okay, so if we give Control P, no, technically it asks again for this. So why the hell it's not? What is it complaining about? List out of range. Ah, why? Okay, let's print licked. Foo is equal to licked. Continue. So I don't get it. This is the stuff. Oh, no, right. This should be returned full. We are still in the first one. Now we continue. We're still in the first iteration, right? Yeah. This program is printed. Next time we hit link, oh, it's okay. So if you guys don't know what is the issue, is because of my receiving here. So my receiving here, actually it get confused between this part here and this part here. So just to make sure I am waiting till this part here, I have to do it with the slash. So not the slash but the closing bracket. Now it should work. Yeah, so now we did go through the first part, and let's continue again, see if it's gonna continue. Okay, it did continue and did leak the second address correctly, and it did calculate correctly. Technically it should be right now the REP. Let's take a look. Info frame, oh no, continue first. Info frame, so REP is at this address. I think this is already looking good. Yes, so as you can see, this is the REP that we did successfully leak. Do you guys understand what I did here? As I said, leak and base, you always leak an arbitrary address and calculate based on your wait, let me open VM map again. So for the base and the libc, you calculate based on the starts, but the stack, it's because this addresses, the offset between the address and the top of the stack is always changing. It's not the same, so you calculate between each other. So you just have to find another offset and then calculate based on that. Okay, this is the easiest way to leak an REP. Does it make sense? You see, it's not that much difficult the moment you get a hang of it, right? Yeah, it is okay. I mean, yeah, it is kind of understandable. It's all about practice, believe me. To be fair and honest with you guys, I also didn't have that much knowledge about format string until like a month ago or something. I did the whole model of the printf in Bone College just like a month ago or something, and just then I learned about it. I mean, and I spent around, I think, a week with almost 4 to 5 hours every day, and then over a weekend like 8 hours, and then I understood that, like, printf on a good level. I mean, I did printf exploits multiple times before. I think this is the different part, but I didn't quite understand them. I mean, I can do the basic stuff, but now I can do everything with printfs. At least this is how I feel after completing the module. Because the last few challenges, they are a little bit challenging. I mean, you have to chain it with multiple other stuff. But long story short, if you want to get like a hang of it, you have to practice. I mean, right now I'm just showing you the mythology. So anything that comes after, it's on you guys, okay? Canary is it shouldn't be that hard. I mean, you don't have to calculate anything, you just have to leak it. So I'm just gonna jump over it, right? Is it fine? For the canary, just have to find it in the stack. I mean, just look here. Where's our? Yeah, just look here. Find the like the canary. I think it should be this one or something. I think it is this one, or I don't know. It should be like somewhere here, either this one or this one or this one, and you just like leak it like with knowing the address. And we know now how to calculate the addresses, right? You're just gonna take like an address, take another address, minus, and then divide, and then yeah. So it is this one or this one. I mean, yeah. So there we no. It says this. Yeah. So it is this one. Okay. So it is this one. Yeah, there is also a command to check the canary in GDB GS. No. What was the command to check the canary in GDB? There is a command, I'm pretty sure. I just forgot what is it exactly. I also saw someone in his write-up, he did mention it. Or okay, it will take forever to find it, but do you guys understand what I mean? I mean, I'm gonna give you the T. What do you mean by the leak is without a GDB? I don't get it. Yeah. So the canary is always on the stack. It has to be on the stack. Wait, let me open IDA and show you like where it looks, because it is actually in your program. It is in injected code. Because we have to do challenge 1 after that, so I'm gonna open it. And I think for challenge 1 I have canary enabled, right? No, sadly not. I don't have canary here. I don't see it. Okay, 1 second. Let me open. No. Open new instance. New. this is put in the I mean, in that case scenario, you can use if you don't have the binary at all. Yes, you have to do it purely with the percentage p. But if you have the binary and you have to take a look into the remote, you can use GDB on the remote if you have the binary locally, of course. Oh, so you just say canary? Oh. Yeah, okay. Never mind. So you just write canary and then you see where is the value of canary. So this is the canary and you can see it here, okay? There is so much commands and there is no way you can remember all of them, especially when you start doing heap, because heap, there is just so much stuff. Like there is so much stuff you can do here, to look at the chunks, to look at what was allocated, to look at the fast bin, to look at a lot of stuff, because the heap is one of the most complicated and advanced topics in binary exploitation, and they have literally a lot of stuff and a lot of commands. So yeah. Yeah, but to make sure you know where is the canary, just run canary, Matthias. I mean, just do canary and then you will find it. It's here. And then just look at the stack like this and you find it there. It's here. So now you have this. Just take it, pum. Just take this again, pum. And then just do minus, divide by 8 because it's the size of each it's the size of the parts of the memory layout. And then you can just find the index and just leak it. I think it should be fine so far, right? Okay, I will continue. This was challenge 1. Let me close challenge 0. So this was challenge 1, and in challenge 1 I did give you guys the win function. The win function was yeah, so to actually be able to yeah, so basically to get like the secret message, you have to overwrite the vault value with this value here. I mean, this was like the whole point. It was, I think, in the check here. Yeah, check. Yeah, no. Yeah, this was just some stupid stuff. Yeah, here in the win function, it's being called here, and you just have to override the value of a vault code to that thing. And the value of vault code, you don't have direct access to it, as far as I remember. Yeah. So we just have to overwrite it ourselves on our own. To not repeat the same code over and over, I'm just gonna take this and paste it here in challenge here. Just gonna do, now we finished with this challenge, so we're gonna go to challenge 1. I always like to run the challenge first to see. Okay. Oh, I messed up this part. So it is asking for the code, and I think this part here is useless, right? It should be this one, can't be. Yeah, so this is the percentage p and it is after this thing here, so we don't need this part here. We will leave this ABCs here. The indices we're still not sure of. The return, I mean the stuff that we will get back will be separated by this, yeah, this. Then it is gonna, let's just strip it to remove this space, because you can see space here. Strip it, and this should print us this stuff that we get here. Don't need, yeah, okay, let me just print it here before returning, and just for now get rid of all of this, or just edit them like this. Now we have print leak function, and then we're just gonna give it p, and then we're just gonna give it, I don't know, maybe just the index 1. Yeah, yes, that secret was a global variable. Yeah. So by the way, if it's a global variable, it is mostly in the BSS section, and the BSS sections, they have specific addresses that we can then just put on the stack, and then we can leak them. Okay. But we will see, we will do all of this in a while. For now, we're just doing like the first setup on the binary. We're just like trying to connect and do like the connecting with the GDB, and then we will start like looking into how to actually do it. Okay. Yeah, so we have to find the right prints now. Let's do GDB chal1, and now we do this as a win or a main. It was main, right? You take a look into this again. Yeah, so it was main, and it was this thing here, as you can see it here, and it was 1595. 1595. It is this call here, and we can just take this part here, pom here, and again we're just gonna continue from the start, and then we're just gonna single instruction to enter the printf itself. Standard AAPB CCs to know what is going on inside, and yeah, I think this should be it to give us to not result. Yeah, should change the name of the binary to what? Okay. I'm splitting this thing here, and it does not like it. Maybe because I am. What am I returning? Print leaked. Oh, it is actually reading this part here. What the hell? Why is it reading this part here? Oh, it's again because of this thing here. Okay, let's write code to tell it that we want this part here. Okay. Run it again. First, come on. Time is actually flying. Just going on. Why is it reading the remote target? Did I mess up something here? Okay, I think I'm messing up something, so I'm just gonna do context log level. Just gonna put it on debug to see what the hell am I sending, and because it's just it is blocked somewhere. Stop it like this. Continue. Okay, so I'm receiving all of. Yeah. Okay, let me remove this here. Okay, security level. So we received this bunch of stuff. One second. Why is it stuck in code? What do you mean, donk, by a random message depending on the level number? I mean, it shouldn't matter, right? Wait, let me run it with GDB again. GDB. Run. Yeah, it just gives the same thing. I mean, I'm not trying to stop here. I'm trying to stop the code here. No, I don't see shit. It is actually stuck here. It doesn't reach this part. Okay, let's see receive all. See what is everything we're receiving. Why it stops in the security level? Why it doesn't go under security level? It's updated, and then we have log access attempt. Okay, now I actually reached that part. Code. This is again stuck. What? It is breaking. This breaks for some reason. There is no BSS in the start. Okay, let's try to do something. Get rid of all of this and start from fresh. P receive until I never saw this type of error before. It's not even an error, it's just stuck. It does not continue, that's the problem. It is literally stuck. Because it's trying to, like, it is saying reading libc from remote target. It is literally breaking here. Or again, it's breaking level, security level. Oh, why is it breaking here? I don't get it. Because of this random. Yeah, it's stuck even with interactive. I mean, GDB is stuck, but not this instance are here. No, I'm just sitting. Oh yeah, we can just get rid of this. We can just continue. Nothing else. It is reading, like you see, it's trying to read some stuff from the backtrace. It is doing some weird reading, you see. fgets. It is literally stuck in the fgets here. Yeah, as I said in the beginning, it is stuck in the fgets here. I think the BSS, the way it is implemented in GDB is not the same. I see. What if instead of doing this, we do first, is process working? Yeah, process should work. Yeah, process is working. So if we do process and we do gdb attach and we do p, was it like this? I don't remember. Yeah, okay, now we are getting further. Continue. Yeah, okay, so the attach is working. I don't know. Yeah, I don't know why the gdb debug, but I'm pretty sure it has something to do with this bcc start. Like, this is breaking it for some reason. I don't know, but I will take a look later into this. Okay, now that we know where is the issue, we can go back to our previous code. No, not this, this. We can I'm gonna get rid of this, get rid of this, and make here C and no, E. Alright, the whole code for better readability. Don't have to print this. Time to decode it. Let's see if it works. Yeah, okay. It seems like no, actually even here it's broken. It's a read overflow. It is again breaking in. Are you sure it worked for you, Easy Plays? I will check your script. But you sent me the challenge 00, or you sent me both? They are in the same file? I don't see the other one. I will try to do some tricks to continue, because it will wait, and this will get this is already getting on my nerves. I will check your script, Matt. But your script is also for challenge 00. Let me check the solution of the it is correct, it's working. Now let's see if we modify this and we put target GDB, and now it's gonna break. Attach debug. So the debugger is broken, but the process is actually working fine. And I assume you used purely the percentage %p. You didn't use the debugger at all. Yeah, okay, true. Okay, yeah, we can do that as well. To do this, I think it was process pause. Okay, I can just do okay, nice. Sit remote in GDB. Target my target remote 510. Why? If this doesn't work, we're just gonna go continue to challenge 2. Sorry guys for the convenience, but it should be the same idea. Just instead of overwriting the variable in challenge 2, we're gonna overwrite an address. Never had to start a server. What the hell is this? Just Okay, finally. Yeah, so let me just get rid of this and start doing this. Yeah. So now we can continue, right? And then we do percentage p. This is also breaking. Are you guys sure that it worked with you? The GDB? Is it also only on my side? Because this is technically just trying to debug this process remotely. Anyways. Challenge 2 is 100% working because I tested it already. And this one, I don't know why I didn't. Yeah, okay. Is it fine with you guys if we just go straight to challenge 1, challenge 2? Because the only difference is that now here in challenge 1, what we were trying to do, we were trying to overwrite this vault code with this, right? And to do this, we did put the address of vault code on the stack, and then we did try to overwrite it with this. Now we're gonna do a different thing. Now, for the challenge 2, we're gonna try to overwrite the global offset table to inject win instead of a function. So in my case, I did set it, I think, instead of memset or string. I don't remember, but we can memset, I think. Yeah, I think it was memset. Yeah. So I just did modify this memset, the address of it in the global offset table, and did modify it with the other variable. But in both challenges, you have to use like a control N to solve the challenge. Okay. So we will try to start fresh and do it like solve 2. Let me just take the prologue from this and I'll repeat everything from scratch. We can get to these again. I will show you how to get them, but these we will do them again. Bum. Also this, also this. Yeah, we will do this part again. Plus equal b, make a bunch of a's, b's, just like this, or we can put them here, just use them, just put them here, and here we can just put control p, and now we're gonna do the same setup we did before. So gdb, change this gdb debug, yeah, no, Python 3. What am I doing? Solve 2. Why is everything breaking today? Oh, yeah, okay. It is still running on this instance. Let me close this. Why? Oh, my bad. Yeah, okay. Now it's actually starting. Now it's going good. It is going good. Yeah. I think this address was correct, right? I'm just gonna make sure these addresses are correct. 192, 192. Yeah, in fact. Right. 192. Yeah, so it's actually correct. This is the printf that we had here. So the main is actually calling this function func, and inside this function we are running in a loop, and within this loop we can keep calling printf with our format specifier every time, and we can start like doing our leaking and whatever we want here. I would try to solve it in one try, like in one run of while loop. I would try to modify everything, but you can also try to do it like in multiple rotations. Like the first rotation, no, it's not gonna work in multiple rotations, because the moment you're gonna try to modify anything here, it's just gonna break if you don't modify anything outside. And if you try to modify anything outside, there is not that much options. There is maybe this option here, but this option here will not work because of this part here, because we are calling puts here, not only here. So do you guys understand what I mean? Because I think some of you are still confused. Okay, so basically we have something called the global offset table, right? This is global offset table, and you will see it now. So now we are running already our code. So if we do code, you see all the entries in this global offset table. And these entries are the translation. Puts is just like printf. Puts just does, it's not a variadic function, it just prints a string. It's like printf, but puts does not have format specifiers. That's the only difference. So we have this global offset table entries, and if we do checksec, you will see that the rel row, which is the protection of global offset table, is only partial. Partial means we can overwrite these entries. What I mean by this is we can modify these addresses, like for example what is memset is pointing to, and we can point to something else. No, so we will modify this address. This is a mapping, so we have the absolute address and we have the relative address. This relative address is no, sorry, this is the absolute address inside the libc, because memset it exists in libc, and all the goat entries, they are in libc. You don't find here the same function that you see in info functions. Like it's not info func. Yeah. So what you can see here you see gdb so to no gdb shall to info functions. So what you see here we see all the functions that are used in the program. And when you see PLT here, it means this function is not local. It is a function inside the libc, and we have to call it through the global offset table. This is the mechanisms used to translate the functions from a global offset table to something readable inside your code. And some other functions like func and main, they don't have this PLT because they reside within the program itself. That's why and here, like, we cannot see the global offset table because the program is not run, so these are not resolved yet. And as you know, the linking is happening in the runtime, not in the compile time. So yeah, that's what I wanted to mention. Now we will run it again, like this thing here. As you can see, global offset table, we see all here the functions, and as I said, our main goal here is to try to overwrite this memset. So basically, instead of having this address here, we should try to have it have another address. And to do this, we're gonna look for this address because it is where this address resides. So here we have like mapping, so we have here addresses. This is the global offset table. It has like addresses. For example, here memset, it is 40 28, and this 40 or 28 will be resolved to this address, like this address 78 whatever. This address is in the libc, and the moment you call this memset, the global offset table the global offset table gonna resolve it on his own. Okay, this is not something you do. So our goal now is to actually try to modify this part here and to make it, boom, look at our win. We have to make this address pointing into win. We already have the address of win. I mean, I have it from here, but if we go a little bit on top, if you go a little bit on top, yeah, you can see it here. So you see the address of win. This is the address of win. So this address, we have to inject it somehow here. This is our goal. Do you guys understand what is goal of this challenge? Yes, exactly. As I said, it is a mapping. So we have the addresses because, listen, this global offset table, it resides in our code, right? As long as it resides in our code, it is in the memory. And as long as it is in the memory, it's like this. So we have our REP. REP has to find this address somewhere in the memory, and this address, when it is trying to be translated through the global offset table, it will jump to win. So it's like we have two jumps, but you don't have to care about this. This thing, we don't have to modify it. We only have to modify where it is pointing, so that it actually starts to point at our win. Is this clear, guys? You have to try to imagine it, because otherwise it's, yeah, I'm not sure how to explain it in a better way. It is, as I said, it is a mapping, so it's like a mirror. The moment you try to call memset, of course it has to have an address inside the binary. This is the address inside the binary, so the moment it is the moment you try to call it, it will be resolved to this. And our goal is to basically, instead of resolving to this, is to resolve to something arbitrary that we control. And to do this, first of all, as I said, we have to find the addresses. So we found the addresses. You see here that I have mem1 and mem2. The reason for that is that this is actually I think this is 8 bytes. No, we don't have to do it. Listen, what I'm explaining here has nothing to do with linked list. This is a real mapping. It's like a table. That's why it's called the global offset table. So it has nothing to do with the linked lists. So going back to what I was explaining here. So the reason why I did split the memory into two parts is because the %n, this thing here, it can only write 4 bytes. So this thing can only write up to 4 bytes. But here we cannot, this is not going to work here. Why? Because we have more than 4 bytes. So imagine we are able to write 1, 2, 3, 4 bytes. This part, if they are not modified, if they are not put to 0, we're going to be pointing to something completely different than what our goal. That's why I did split the writing into 2 parts. So my first part was actually doing it in the other way around. So I did overwrite 1, 2, 3, 4, like this thing, 4 bytes here. That's why you see the difference is just 2 bytes. So 8, 9, A. So mem A is pointing to this part here, and the mem2 is pointing to the start from here. Again, let me explain it here. So our address is 7, 8, A, B, FCD894000. And as we said, this thing here, it is in an address, right? It is running, or it is lying, or it is residing in this specific address 48. And we know that every address, it has one single byte. So if we go further down to 444429, it will have 1 byte again. So here, what do we have? We have 00. We have here 94, and we're just gonna continue. So on 3A, the address 3A, we will have D8. And the moment you read this address, you are reading it this way, always. Okay, so if I, instead of reading 404028, I read 4040 no, this 2A should be. So instead of reading 4042.8, I read 4042A. I will read only this part, which means I will only be reading this part here, which is 1, 2, 3, 4 bytes. That's why I did split the injection that I'm doing into 2 parts. This part here, I did modify it alone on its own, and this part here again modify it on its own. And why did I have to put both of them in the memory? Because printf cannot operate on stuff that you don't know. I mean, you cannot put only one and then like just increment it. You cannot do it because the address you're trying to overwrite has to be on the stack. Because %n, what it does, %n, not %n, what it does, it looks at the first occurrence of the first argument of it. Like if we have here %s, the first argument is going to be taken by %s, the second argument by %n. So this element here is going to be overwritten by whatever we are writing here. This is how %n works. So the moment you try to overwrite it, you have to actually overwrite it with the right address. That's why I did split it into 2. Do you guys understand why I did do this split? Yes, because %n does not allow you to write 8 bytes. Yes. I mean, the other way of doing it is to actually split it like this. So 1, 2, 3, 4. So you will write these 4 bytes first, and then you will write these 4 bytes on their own. And to do this, you just have to update these addresses. So instead of having 2A here, you have to have so 8, 9, A, B, C. So you have to have 2C instead of A. And then you will overwrite these 2 bytes. And of course, you have to modify also how much you are overwriting. And now to be clear, to overwrite 4 bytes, you use %n. To overwrite only 2 bytes, you use HN, which is half n. And to overwrite only 1 single byte, you use HHN, which stands for half n, which is only 1 byte. I mean, you can also do this challenge by overwriting every single byte on their own. Like you can overwrite this alone, but then you have to put all the addresses on the stack. So then you have to have 1, 2, 3, 4, 5, 6. So you have to have 6 addresses on the stack to do this. Yeah. Does it make sense so far? We are running on late on time. I think the part of leaking should be already it should be already easy peasy to do. The only difference is instead of doing this directly, you have first to do it with P. So first, before doing the N part, you have to do it with P. So the moment you do it with P, and now look, this is really, really important. The moment you do a single modification here, it will mess up your stack. So if I do here just p instead of np, I have to update this to 3. Because otherwise these 2 bytes going to be pushed down. And you will see, if I leave it to 2 and I run the binary again here, look at what will happen. Oh, look at what will happen. Why this thing is crying again? Ah, yeah. Look at what will happen again. Yeah, so I have this thing correctly. SE, now I'm within the printf, and now if I do x50 xg and then I do rsp $rsp, why this tag is empty? Is it further? Anyways, I'm not sure why the stack is empty, but you see that the addresses were messed up now. You see that this address, look, 40, 40, 28, and it has like the 2a here on this part. Look when I update this to 3. Like this thing here, it just makes sure that the addresses are aligned, because these addresses, they have to have a valid index, and to have a valid index, they should take a whole space, like a whole position. Like now, look, we will rerun it. As you can see now, look, the addresses, they have like a right offsets. They have the correct place. And I think, yeah, so you see that they have the right offset. And here you can clearly see that the offsets are actually no, it's actually correct. So 5 minus 11 minus 5 is 6. So 1 2 3 4 5 6. Oh yeah, so it's actually correct. So and the reason why this function does not have that much stuff on the stack is because we are not in main anymore. Main is the one that have like a lot of stuff there. We are inside a thunk. So so yeah, so that's why this is 11 and this is right below it 12. It's because this is here. Doesn't make sense that these addresses are correct. Now if we continue, technically, you see I have like right now my percentage p is actually printing the addresses correctly. This is like the first part. You never jump into the n before doing the p correctly. Like now that my p is actually printing the stuff correctly, you see? Yeah, this one is actually this one, the 12. Yeah, because you see the 3 b's are right after. This address here is somewhere on top because we did print here. Look at how many spaces. Like here there is a lot of bunch of spaces that were printed just so that we can override this part correctly. And you guys should understand why we do this in a minute. Let's go back to our painting. So as I said in the beginning, let me just go back all the way. Yes, so as I said in the beginning, we have to overwrite this part alone and this part alone. We have to overwrite like our target address. What was it? It was 4013 AC. So this what we should have at the end, 13 AC, which means this whole part should be changed with 40. How to do this? We just have to print 0x40 spaces with x spaces, and this part's just gonna be injected here. Does it make sense? So 40x, if it's combined with n here, it means we want to write this 40 on this place here, because we have this address. This address is this part here. So n already got the specifier that points to this address here. And as long as we have the specifier pointing to this address here, this overrides here is actually overwriting this upper part. Do you guys get a feeling of it? Does that make sense? For the second part, it's the same. Like this part here, to do like this one 13 AC, it's the same. The only difference is that we have to deduct what we did right before. I mean, the reason is simple. We want to write this part here, but this part here, you have to count also what we did right before. You cannot just go further down without counting, because percentage n just counts everything before it. This is really tricky. Percentage n counts literally whatever comes before. Doesn't matter what we have before, all of it will be counted. That's why you have to deduct it back from here. And this thing here will eventually overwrite 13 AC to this part here in the global offset table. Do you guys understand? Does it make sense? The moment you understand it, it works like magic. Also, by the way, this two addresses, you can also put them here at the beginning. But if you put them here at the beginning, you're not going to be able to see them in the debugging, because printf, I will tell you why. Because this was also one of the errors that I tried to do in the beginning when I was still learning printfs. This address, it is not only 4013 AC. It has here a couple of zeros. And printf, as you know, it stops when it finds a 0. So that's why your printf is not going to be able to print everything, even though it actually processes everything, but it's not going to print everything because of the zeros. That's why always the addresses keep them at the end. Even though, like, why is it better to have them at the beginning and not at the end? Is because now let's imagine this scenario. We have them at the beginning, right? Now we are writing here some more stuff in our exploits, like, I don't know, some payload, whatever. Now this payload, whatever that we add here, is not gonna mess up the offsets that we did put here, because these offsets, they are not pushed under anymore. Exactly, these offset, they are on top now. They are not pushed down. These offsets, they get modified and they get pushed down because we are putting some stuff below them. Under them, sorry. If they were to be under whatever we are writing, their offset will never change. But as I said, we always want to have this mixture between what is more practical and what is better. This is more practical because we can clearly see where are the addresses and we can test them on the fly before actually doing them. And this is wrong. It should be here because we have the thingy. Okay, do you guys understand? So now I will put this back to 2 and I will put this back to n because I'm only overwriting 2 bytes, and this, like a charm, will solve the challenge. Let's check the global offset tip. Oops. Global offset. Like something happened. Check a global offset table. As you can see, memset is actually correct now. But now let's do NE. NE is the next instruction. So basically, I'm not gonna go inside the printf, but I'm gonna jump over it. Now if we do NE and we do global offset table, ta-da! You see? You see how this was overwriting? All of this was overwriting just within the scope of this this run, like this here. So what I did is I did breakpoint here, and I just did jump just right over it, just to the next instruction under the printf call, and right under it. We can disassemble the func again. Right under it, as you can see, I'm right below the printf. It did modify the global offset table, and it is right now pointing to our win function. See, now the moment we will hit memset here, because we are in a while loop, so it's gonna go forward and just reach this point again, and the moment it will reach this point, it's just gonna run our win function. So if we continue, as you can see here, flag full, it worked. Doesn't make sense, guys. Uh, and with this, I think we will end the lecture. It's already way over 2 hours. I try to go as simple as I can. And the same idea is used in the previous challenge. I mean, this challenge here. Just instead of overwriting like memories of addresses, you have to have here the address of the variable itself. And actually, you can do like a lot more crazy stuff. Like instead, like if we don't have when, we can actually create our when function on our own with the roping. In the future, we will do the return-oriented programming, and we will learn how to use it in like a lot of scenarios. We will learn how to use it with printfs. We will learn how to use it with buffer overflows and things like this. Yes, you can do literally everything with this. I will supply literally everything today at night, including this lecture. But try to solve it on your own. Especially like challenge one, I didn't do it with you guys. Try to do it on your own. It should be the same idea. So you're just gonna have the you're just gonna find the address of the BSS, like the variable, where it is used. Yeah, so this vault, as you can see, it is coming from here. This is like the address of it. So you're just gonna put this address on the stack and modify it. That's it. So this address in this setup, this address here, it should be technically here, like somewhere under here. And then here you just have to find its offset with %p, and then voila. Just the problem with this one here is we have 8 bytes, so you have to do again 2 overwrites. So you have to put both the addresses of this and this +2. So yeah, I will provide literally everything. I'm gonna also add the script of the others into everything before I push it. I will push it later today at night, okay? Just try to do them on your own. If you don't understand, rewatch this lecture, and you should be good to go after that. Plus, I think we will upload both of these videos on YouTube. I think I will upload them on YouTube as well. I don't think I'm gonna upload them on Google Drive anymore. I will add them on YouTube. I think it's better for everyone. What? What do you mean, T? What do you mean by what do we need for real? You mean how to use this in the wild? Also, easy place. It's just a matter of practice, believe me. The next Friday you meant. Friday we have the auto reversing. So you guys also gonna receive 3 challenges from me. The third challenge, to be honest, I'm not confident if anyone will solve it. The only hope that I have is on Donk. I really hope you will solve it, man. Because I don't know, it might be a little bit difficult. I can tell you a little bit about I can tell you guys a little bit about it. So basically you have 100 binaries that you have to solve all. So you have to solve all the 100 binaries, but if you check them, you will see that there is some similar patterns, and you have to automate everything. I mean, that's also the name of the next lecture. So it's automatic reversing, and in the following few weeks you guys gonna learn how we can automate all of this. And yeah, so that will be it for today. I hope you guys did understand and learn a thing or two, and I will see you guys again on Friday. Okay.